A recoverable error condition is a problem that can reasonably be rectified. Some recoverable errors can be addressed automatically. Say that your attempt to acquire a lock on a lock file fails because somebody else currently holds the lock. To recover from such a condition, you can retry after an interval. Similarly, say that you're receiving a message over a network which is currently experiencing packet loss. Well, packet loss is expected, it's common, it's normal, and protocols such as TCP provide for retransmissions, timeouts, and so on, and that's all built in. Most of the time, such error handling routines fire and run without the user even being aware of what's happening. But it's also normal to involve the user when handling recoverable errors. Perhaps the network is totally disconnected and experiencing 100% packet loss. The program, under such circumstances, might suggest that the user check the network connection or connect to a different network. Another use case for recoverable error handling occurs in parsers. When a parser encounters a syntax error or some other glitch which it is hopelessly confused by, it can back out and retry the parse again, this time with looser settings and a lesser goal, to get as far along as possible in order to produce the most sensible error message it can from what content it can understand. And sometimes the user is directly responsible for an error. Perhaps they provided nonsensical input which the system cannot reasonably deal with, such as a rider mounting a bicycle backwards. To recover from such a condition, you can inform the user what has gone wrong and suggest a possible remedy, gently guiding them onto a path towards success. The two dominant mechanisms for handling recoverable errors are return codes and exceptions. Both have been around for decades. Both remain popular today. Both approaches can be done well, but in both cases, programming language designers have learned from the challenges encountered by their predecessors how to do them better over time. Let's imagine a C function foo, which illustrates basic use of return codes. Foo performs some task which might or might not succeed. To communicate to the caller whether or not it succeeded, foo uses a return value. It returns 0 on success and non-zero on failure. The caller is expected to inspect the return value, and in the event of failure, to perform whatever error handling the programmer deems necessary at the specific call site. Here, a simple message is logged to standard error, and then program execution continues. One notable quality of return codes is that they're simple to implement. They don't even require support from either the language or the runtime. If you're feeling frisky, you can write Java methods which return -1 on failure rather than throwing an exception. Not that you should, because that would be counter to Java culture and would violate the principle of least surprise, confounding Java programmer expectations, but you can. It's completely feasible because the only requirement for implementing return codes in your project is language-level support for functions which return values. That's it. Here we have a Java snippet with identical behavior to the C snippet on the last slide, but this time it's realized using exceptions rather than return codes. An exception can be thought of as an alternative return statement. When the function succeeds, it uses the primary return mechanism and hands back control to the caller along with return values, if any. However, should an error condition arise, the function instead uses the secondary exceptional return mechanism to throw an exception value to the innermost catch block in the call stack along with program control. If the closest catch block is a ways off, then the throw will have to sail over multiple stack frames, cleaning them up as it goes via a process known as stack unwinding. Many exception implementations provide a stack trace. To do this, they must traverse some amount of the call stack, not stopping at the frame, the catch block, but continuing some amount further towards the outermost stack frame in order to provide a trace with lots of useful context. However, even though stack traces are closely associated with exceptions, they are optional. They can often be disabled or replaced. They might be configurable via a stack trace depth setting. Responsibility for stack traces can be assigned to logging facilities rather than error handling facilities. And one good reason to do this, well, assembling stack traces, traversing all those stack frames and performing all that string concatenation, it's expensive. Exceptions have a reputation for being slow, but the main culprit is typically the production of stack traces, not exceptional control flow. And so, the essential quality, the fundamental characteristic of exception-based error handling is not the facade of the stack trace. Instead, it is the alternative return mechanism of the throw. Here we have another Java method, not 42, which guarantees that the number you pass it is not 42. Then hands back whatever non-42 valued number you supplied as its return value. This function has two possible return types to go with the two return paths. On the normal return path, not 42 returns type int to the caller. On the exceptional return path, not 42 returns type illegal argument exception to the innermost catch block. That's what the throws clause, highlighted in red on this slide, tells you. It gives you the return type of the alternative exceptional return path. Having two return paths makes control flow more difficult to reason about, which is one of the principal drawbacks of exception-based error handling. In contrast, with return code-based error handling, control always returns to a single location, the call site. That is, the precise line and location where the function was invoked. So the flow of control is comparatively straightforward and easy to follow. So far, we've been looking at checked exceptions. When we say that our exceptions are checked, that is generally understood to impose two constraints. And here I will accept arguments from the from the audience as to what actually qualifies as checked exceptions, but these are the arguments. This one is mine. First, the fact that a function may throw an exception is part of its signature. Changing a function which doesn't throw to one which does is an incompatible breaking change. Furthermore, when the type of exception a function may throw is specified in its throws clause, and note this is not a requirement for every programming language, changing the function to throw a different type of exception is also a breaking change. So if we change it from illegal argument exception to throws, file not found exception, that's a breaking change. This makes perfect sense when you consider that exceptions are just alternative return values. Changing the main return type from type int to type string would be a breaking change, of course. Why wouldn't changing the secondary return type from one exception class to another, why wouldn't that also be a breaking change? Second, when a function contains a call to another function which throws, the outer function must either catch and handle the exception, or it must specify in its own signature that it throws. And if the exception type is specified in the throws clause for the inner function, that exception type must also be propagated via the method signature for the outer function. Here we see that the method body for our guessAnswer method contains a call to not 42, which we have seen previously may throw an illegal argument exception. As a consequence, the method signature for guessAnswer must also specify that it can throw an illegal argument exception. With unchecked exceptions, used in many popular languages including C#, C++, and all the major scripting languages, Python, Ruby, PHP, Perl, etc., those constraints are all dispensed with. There is no throws clause included as part of the method signature. So you can't tell which functions throw exceptions and which don't. And there is also no exception propagation. So if a function which has not heretofore thrown exceptions changes its internal implementation to start throwing some, there's no way for users to know that, at least not from the function's API. The result is that in projects written in languages which provide unchecked exception-based error handling, any code, anywhere, can throw an exception at any time, which sounds bad. And yet, unchecked exceptions are extremely popular. So why is that? Well, part of the explanation has to do with the domain of programming that you work in. If you're a systems programmer, your stuff has to be locked down, and the author of the article that I'm presenting tonight, Joe Duffy, is a systems programmer. His article is, in fact, about the error model for an operating system, and you don't get more systems-y programmery than that. From the systems programmer perspective, having code that can throw exceptions without warning at any time is disturbing. But if you're an applications programmer, unchecked exceptions offer one glorious benefit. They allow you to pretend for a while that errors don't happen. And thus you can write code without having to consider failure modes, simplifying the problem space and yielding an increase in development velocity. This approach has its problems, which we'll get to in a minute. But let me make clear, increasing development velocity is incredibly valuable and important, especially from a management perspective. Also, sparing programmers from having to write a lot of boilerplate error handling code makes them happy, which is also valuable from a variety of perspectives. Naturally, code written while pretending that errors don't exist accumulates technical debt rapidly. But accumulating technical debt rapidly is not necessarily a problem, especially when you just need to get a minimum viable product out the door. Lots of code gets thrown away or rewritten from scratch, and the less you spend on code that is destined to be discarded, the better. And the usual approach that people take with unchecked exceptions is to wrap a giant catch block around a big blob of twitchy, fragile code rather than spending development time on managing fine-grained error handling in the innards. And you know what? It pretty much works. It's expensive to maintain, as those of us who have inherited such code bases can attest. But lots of sufficiently reliable application software gets written this way. Not everything has to be bulletproof. What is a problem, though, is that the technical debt acquired by pretending that errors don't exist is unusually expensive to pay down. That's because it's not easy to look at a code base which uses unchecked exceptions and know where potential failures may occur because the code base contains no evidence of them. This invisible control flow issue is particularly challenging when trying to harden code bases in C#, Python, and so on against failure, but it afflicts even some implementations of checked exceptions such as Java's. The crux is that when you look at the call site, there is no indication that a call might throw. With checked exceptions, you can see what a method throws from its signature, but that's way the hell off in some other file. At the site where the function is actually called, you will find no such indication. Swift and also Midori both use exceptions, but they both solve this auditability problem by requiring a try operator before any call to a function which can throw. If the call succeeds in this example, the assignment operation completes. If an exception occurs in the called function, the operator then passes that error up the call stack using the exceptional return mechanism. Go, Rust, and Swift all provide explicit error handling and represent a trend away from the anything goes uncertainty of unchecked exceptions. But, as we will see, they all provide significantly improved error handling ergonomics, and so rise to the challenge posed by unchecked exceptions vis-a-vis development velocity. Even if those languages don't allow developers to remain blissfully ignorant about potential failure modes, they make dealing with them, or they can make dealing with them, or putting off dealing with them, less painful. You get a code base which is marginally more expensive to get up and running, but which is significantly easier to maintain over time. Because all the spots in the code base where failure can occur are identifiable. Being able to audit your code base for operations which may fail makes it much easier to manage technical debt. For completeness' sake, I need to mention another mechanism which is used to handle some cases of recoverable errors, and that's signal handlers. What the program on this slide does is loop endlessly, waiting for you to press Control-C, at which point, rather than terminate the program as you would expect, it prints a message, haha, and keeps running. You can use send a kill to kill this off. Other than that, don't run it on your machine. It achieves this capability by registering a signal handler which catches the SIGINT interrupt signal sent when you press Control-C by the operating system to the program. This custom signal handler replaces the default process terminating signal handler installed by the operating system for SIGINT. And that signal handler up there, the replacement, one looks an awful lot like an error handling routine, right? And in some sense, that's what it is. However, signal handlers are global. There can only be one for each process for each signal type. As a consequence, signal handlers are not composable. Additionally, signals can be sent to a process at any moment. That is to say, signals are asynchronous, which is quite different from return codes and exceptions, which are synchronous inline mechanisms. When a signal is received, the system saves the current execution context from the processor onto the stack and pushes a new context onto the stack optimized for the signal handler, where the signal handler will now execute. Superficially, it looks a lot like running an ordinary subroutine, but a signal handler typically has a lot less information available to it in comparison to error handling code, using return codes or exceptions, because you typically have to resort to passing signal handlers useful information via mutable global variables. Yuck. And for all these reasons, signal handlers are not appropriate for general error handling, and in modern times do not present a valid third alternative to return codes and exceptions. Now that we've seen recoverable errors and talked about the popular techniques for handling them, let's talk about bugs. A recoverable error, again, is a problem that can reasonably be rectified. A bug, in contrast, represents a fault in programming logic. It is something which the programmer has not accounted for, and after which the program may do unplanned things. Consider the state of a C or C++ program after there has been an invalid write beyond the end of an array. What happens now? Well, if you're lucky, the write attempt happens consistently at a memory address the system considers not writable, in which case the program will terminate immediately with segmentation fault or similar. If you're unlucky, and you probably are unlucky, then the bad code is only observable through its secondary effects. For instance, the bad write could corrupt some innocent bystander data structure which happens to reside in memory adjacent to the array. The effect of this bad write will not become observable until that corrupted data is accessed once more, which could happen soon, or never, or at different times on different programming runs, especially programming runs where you have recompiled with a debug print statement in order to figure out what on earth is going on, and an invalid read is not much better. Say that you're reading from a memory location which is supposed to hold a count, which typically ranges from 0 to 100, and your intent is to assign the value that you find there to a variable, local variable. Say that you read from a bad location instead, which happens to hold a pointer value, a memory address. Now the value, which is supposed to be no more than 100, might be a few trillion, give or take. Again, if you are lucky, your program might give you some immediate reproducible failure, but you probably aren't lucky. Another kind of bug is unintended integer wraparound. As with invalid memory access, integer wraparound is handled differently by different programming environments. In C, signed integer overflow is undefined behavior. In Rust, it's an error in debug mode and left unchecked in release mode. Unlike invalid memory access, sometimes wraparound produces perfectly acceptable results. So what should the default behavior be? Well, people disagree, but I'm going to assert there's one right answer. Integer wraparound should be considered a bug because unless the programmer has specifically indicated that wraparound is desired. And the reason that it's a bug is that we have observed over many years that unintended integer wraparound often results in serious security vulnerabilities. In fact, one was published just this week in a client library for RabbitMQ. Once a wraparound occurs, we should assume that our program may do something that we do not expect and did not plan for. For instance, there might be a conditional test on the integer which assumes that it falls within a given range. Now that it's wrapped around, that assumption is violated. Divide by zero is another classic bug. How should a program behave after a divide by zero? Well, is the purpose of your program something absurd like proving that 1 is equal to 0? If it's not that, well, how do you know that your program is still going to do what you want? And what should happen if some assert code fails in production, assuming you have assertions turned on in production? The whole point of an assert is to guarantee that the world is as you think it is. If, in fact, the world is something else, can you know what the program will do? Let us draw a key distinction. Bugs are not recoverable. In well-formed error handling code, or well-formed handling code for a recoverable error, the programmer has anticipated all possible failure states and specified how the program should respond in each and every case. But a bug, by its very nature, introduces a state which the programmer has not anticipated and has not accounted for. That unanticipated state may or may not result in visible failure because a bug is a necessary but not sufficient condition for externally observable failure to occur. But once the bug has been encountered in the program, the future has become uncertain. And a trend we have seen in recent programming language design is a move towards providing distinct error handling mechanisms, 2 of them, with a clean separation between them, 1 for bugs and 1 for recoverable errors. And the article I'm presenting tonight, by Joe Duffy, once again, describes the error model in Midori, an experimental operating system developed at Microsoft from 2003 to 2015. In Midori, bugs are handled via quote-unquote abandonment, which tears down a process, while recoverable errors are handled by a variant of checked exceptions. Go, Rust, and Swift, like Midori, slam a hard wall between recoverable errors and bugs. In all cases, we have a coarse-grained mechanism for handling bugs and a fine-grained function-level mechanism for handling recoverable errors. The consequences of abandonment, and we'll keep using Midori's term abandonment here, vary amongst these projects. In Midori, abandonment tears down a process, which sounds severe. However, Midori was commissioned as an experimental operating system, and its designers had the luxury of building it from the ground up with lightweight processes. Multiprocess apps in Midori were the norm. So abandonment would not necessarily, or even typically, bring down the whole application. Think of abandonment as instead causing something like a crashed browser window in modern Firefox or Chrome, both of which are implemented these days as multi-process applications, although that crashed browser window could actually be the JavaScript engine crashing, but you get the idea. The instability is, it's not ignored, but it is contained. At first glance, Go and Rust appear to be less aggressive than Midori because rather than tear down an entire process, Go's panic operator tears down the current Go routine, and Rust's panic macro takes down the current thread. But Go and Rust are designed to work on mainstream operating systems where a process is more heavy than on Midori. And the concurrency story, rather than multi-process applications being the norm, is more typically a single process app with multiple threads. Indeed, one of Rust's main selling points is that its single ownership model allows for fearless concurrency, as they say, with threads. So in fact, you could argue that Midori, Go, Rust, and Rust all provide roughly the same abandonment functionality, just tuned for different assumptions. They all tear down, let's call it, one unit of concurrency, where a unit of concurrency is either a thread, a go routine, or a lightweight process. But they expect to avoid bringing down the entire application unless that application happens to be single-threaded, in which case the only thread is bye-bye. So the outlier amongst this quartet is Swift. In iOS, single-process apps, optionally with threads, are the norm because that's copacetic with the iOS sandboxing model. It's really hard to get processes to talk to each other in iOS. However, Swift's fatal error routine is completely unrecoverable and tears down a whole process, meaning that it almost certainly kills the app dead. Swift programmers thus have to be more judicious about using abandonment. Duffy makes the argument that after a bug is encountered, the safest move is to consider the entire process address space potentially compromised and to terminate the process, throwing out the whole address space. That seems rather aggressive, but even if we follow Duffy's recommendations, we're only in a position to offer degrees of safety, not guarantees. Consider that when an assertion failure occurs, the condition that caused the assertion to fail may have already existed for some time. If the bad data was isolated to the current thread or go routine, then perhaps taking down that thread or go routine suffices to contain the error. If the condition that caused the assertion to fail was in memory which was visible to multiple threads or multiple go routines, well, maybe taking down the whole process suffices to contain the error. But it's also possible that bad data was passed around via an IPC message and has compromised multiple processes and their corresponding address spaces, in which case taking down the single process is insufficient to contain the error. You would need to take down the entire multi-process application. But it's even possible that the bug has caused corrupt data to be serialized to persistent storage. Well, now what? Now even taking down the whole application isn't enough. And the point of all this is that the question of how severe the consequences of abandonment should be does not have a single unambiguous answer. Instead, there's a range of possibly acceptable solutions. And I should mention at this point that the debate in Rust over what exactly should be the consequences of a panic, whether there should be a recovery mechanism at all or whether it should be irrevocably fatal like Swift's fatal error, reportedly engendered one of the most heated discussions in the history of Rust development, and the ultimate decision was one of the most controversial ever taken. In summary, our industry has not yet arrived at a consensus on this particular issue. Let's travel back half a century once again and review C's error model a little more closely. Near and dear to my heart because I've done a lot of C programming. The core C language provides no special error handling facilities. However, the C standard library, which includes the error_h header and its associated functionality, establishes precedent and sets expectations about how error handling will be done by C programmers. The primary mechanism is return codes, and let's consider a few standard library examples. The fopen function returns null when it fails to open a file. Then it sets the global integer value errno to a value which indicates the cause of the failure. The fseek function returns a status when it attempts to seek the file handle to a particular location in the file. It returns 0 on success, while on failure it returns -1 and sets errno. The ftail function returns -1 on failure and sets errno. The malloc function returns null on failure and sets errno. The setLocale function returns null on failure, but it doesn't set errno. The assign function, which calculates an arcsign value, returns not a number on failure. It doesn't set errno. Instead, it raises the invalid floating point flag, which has different results depending on how you compile. From these examples, we can discern roughly the classic pattern for C error handling. Carve out a range of values from the primary return type, which will now serve as sentinels, indicating failure, rather than serving as valid return values. As we talked about earlier, One of the nice features of return codes is that, in contrast with exceptions, return codes ensure local handling at the call site, which makes it easier to reason about control flow, and this applies to C for the most part. However, C return codes have many issues. Now we get to the good part. First and foremost, it's easy to forget to check them. Among the many problems with the code on this slide, and I didn't bring a prize for people who can identify all the problems on this slide, but I imagine that people are able to find plenty. Among the many problems with the code on this slide is that the return value of malloc is not inspected to see whether or not null was returned. There should be an if nums is equal to null, then do stuff. It's also easy to make a programming mistake in C error handling code when it exists. For instance, comparing whether a return code is equal to -1 when you actually need to check if it's less than 0. This is API dependent, of course. The problem here is that error handling code is rarely run, if ever, either in development or in production, and code which never gets run is highly likely to contain bugs. The problem of making mistakes in the handling code is greatly exacerbated by the fact that C functions are limited to returning a single value. In order to signal failure in a function that actually returns something, you have no choice but to reserve those magic sentinels, null or -1 or all negative values or all non-zero values or what have you. The result is messy and inconsistent APIs, which make for messy and inconsistent and mistake-prone error handling code at call sites. Another problem is that both recoverable errors and bugs are shunted through the same error handling mechanism of return codes. It's clear why you ought to check the return value of fopen, which opens a file. But do you really need to check the return value of malloc? Probably, and not just on embedded systems. What happens when you calculate the requested memory amount dynamically and there's a bug in your arithmetic? If you request too large an amount from malloc, you'll get a null pointer back, and if you don't detect and handle that, there is probably a seg fault in your future. And I see some nodding heads back there. But many programmers do not go to the trouble of checking the return value of malloc consistently. The default behavior for failing to allocate memory really ought to be abandonment, that would catch some bugs by default by sparing programmers from having to write tedious boilerplate. Optionally, this facility can be augmented with a separate opt-in API which provides for recoverable error handling. In other words, the malloc API as we know it ought to be a rarely used alternative to a primary API which uses abandonment. And modern languages like Go and Rust adhere to this kind of API design philosophy. Once again, they give you a clean divide between the error handling for bugs and the error handling for recoverable errors. But though C uses return codes for both recoverable errors and bugs, it doesn't actually limit error handling to a single channel. Some problems cause signals to be sent to the process. Most notably, if an illegal memory location gets accessed by a null pointer dereference or similar, the C will send a segmentation violation signal, a SIG-SEG-V, to the process, which by default terminates the program. So C simultaneously provides too few error handling channels and too many. And the result is that error handling seems straightforward, but doing it right in C is actually devilishly hard. And C enjoys a reputation for being easier to reason about than C++ and C++'s exceptions. There's a famous article from the author of 0MQ explaining that he chose C because avoiding exceptions in C++ was too hard. But we can also see from, as we can see from how easy it is to trigger a segmentation violation signal in C, you can't really guarantee that C error handling will always be local and limited to the call site. Arguably, the root problem is that it's just too easy to write unsound code in C. Lots of problems that could be guaranteed compile time or runtime errors are not, such as overlength array access. The C language is simple, but the C standard is heinously complicated. And thus, the task of writing sound C code is extremely demanding. Fast forward now to the 1990s and the rise of Java. In theory, checked exceptions, which Java supports, ensure local handling in the calling function, which is almost as good as the way return codes ensure local handling at the call site. That is, the actual line and location where the function was called. However, in Java, certain throwable types do not have to be checked. Specifically, anything which descends from error or runtime exception does not have to be checked. And that actually technically includes the exception class we're using here, illegal argument exception, because that descends from runtime exception. And so, because illegal argument exception doesn't have to be checked, our not42 method is legal Java with or without its throws clause. It turns out that Java not only supports checked exceptions, it also supports unchecked exceptions. And the intent, the stated intent in the Java documentation, is for programmers to use checked exceptions for recoverable errors and unchecked exceptions for unrecoverable errors such as bugs. However, both checked and unchecked exceptions go through the same try-catch-finally handling infrastructure, so there is not a clean separation between them. If you set up a catch block to catch the class exception, you will also catch all the descendants of runtime exception, including null pointer exception, array out of bounds exception, and so on, which is probably not what you want. Java's checked exceptions have proven not to be very popular. And some of the negative reception can be attributed to Java's specific implementation choices regarding checked exceptions, and some of it to inherent characteristics of checked exceptions. One thing programmers find inconvenient about checked exceptions is how you are constrained from changing the internal implementation of a function. If a function's API does not mark it as throwing exceptions, you can't start throwing them, nor can you call another function which throws unless you do one of two things. You can make a breaking change to the function's API, which will have larger implications impacting the API's clients, and might start conversations you don't want to have. Or you can catch the problematic newly introduced exceptions and sweep them under the rug, which is frowned upon but common in the wild. But just how legitimate are the complaints of developers who chafe under these constraints imposed by checked exceptions in Java? Arguably, forcing API versioning is checked exceptions working as designed. They protect the API client at the expense of some cost to the API developer. But Java not only requires that you mark which functions may throw, it requires that you indicate what types of exceptions each function can throw, which dramatically increases the brittleness of the throws specification and the effort needed on the part of the API developer to resolve the checked exception requirements. Now, you not only need to reconcile which functions throw, but you need to either propagate and resolve each one in an accumulation of exception types. And many of these exception types indicate errors that at a high level the user can't do anything about. If a user makes a database query and the database throws a file not found exception, just what do we expect the user to do about that? It's an implementation detail. They shouldn't see that. So the usual recommended solution is for the library author to create their own exception type, like foo-db exception, which wraps all possible internal exception types. So instead of a file not found exception, the user sees a foo-db exception. And the work to do that is a little bit tedious, but it's an honest approach. However, because Java crowds all sorts of things that arise from programmer errors, bugs, into the exception hierarchy, like illegal argument exception and null pointer exception and array out of bounds exception and so on, it takes more time and thought to manage recoverable errors, to write your good catch block. So now, you're not really supposed to declare unrecoverable errors and throws clauses like this not42 method does with illegal argument exception. So this example function is actually somewhat contrived. But the very fact that we are able to declare an unchecked exception type as a checked exception in a throws clause illustrates how the design is all messed up, confusing, and problematic. Truly recoverable errors are actually not that common. Duffy estimates that in Midori, the ratio of abandonments to exceptions written by the people who are developing applications for Midori was 10 to 1. But in Java, all of those would be exceptions. So what Java wound up with is a system which takes much more effort to comply with than pure unchecked exceptions, yet where it's hard to tell whether you successfully lock things down. And so what's the point of all that extra effort then? No wonder Java's checked exceptions have earned a checkered reputation. Swift, like Java, provides a variant of checked exceptions, depending on how you define checked exceptions. No arguments? Okay, well, but Swift does several things that can be seen as solutions to the problems which have become evident over time in Java's implementation of checked exceptions. First, recall that Swift avoids the invisible control problem afflicting Java via mechanisms like its try operator. Second, recall that we also talked about how Swift, like Go and Rust, provides via fatal error a clean separation between handling for recoverable errors and bugs. But it gets better. In Swift, you only indicate whether a function throws or not. You do not indicate what types of exception it might throw. Look at the slide there, and you will see the keyword throws, but a blissful empty string afterwards. Think about what that means for composability. Now you've divided the world of functions into two groups, functions which throw and functions which do not throw. The functions which don't throw can all call each other. The functions which throw can call any function, whether it throws or not, without having to resolve the types of errors that can be thrown. Perhaps it's a bit inconvenient not to have all the specific error types enumerated in a throws clause when you want to catch all the possible errors that might be thrown within a block of code. But Swift's approach represents a significant ergonomic improvement in terms of API design, maintenance, and especially evolvability and versioning over checked exceptions, as people know them from Java. Go heralds a return to the simplicity of return codes, but greatly improves on the ergonomics of C's error model through its support, praise Lord, for multiple return values, eliminating the need for magical sentinels. In C, you would traditionally have to reserve some values from the main return type in order to indicate failure. In Go, you don't have to do that because you can return the error as a dedicated value. Go also improves on C's ergonomics via clean separation between handling for bugs and recoverable errors. Go's error handling is sometimes criticized for its verbosity. The rejoinder from Go's developers and advocates is that planning for failure conditions is an exceptional aspect of programming, and that all that error handling code is first-class code. And they're right, even though perhaps the syntax could be more compact. Despite that, Duffy argues in his article, in my view persuasively, that Go missed a golden opportunity by not requiring that the caller do something with the returned error values, which remain all too easy to neglect. Rust, like Go and C, uses return codes to communicate failure conditions. But in Rust, they are packaged up along with return values into a result type, which forces the user to unwrap values explicitly. Let me narrate the code on this slide a bit. We'll look at the not42 function first. The return type for our Rust implementation of not42 is a result. Result is a generic type, which must be fed two type parameters. That's between the angle brackets there. One must be the type of the return value, and one must be the type of possible error. In this case, the main return type is an I32, a 32-bit signed integer. And the error type is those two parens, which is an empty list or the unit type in Rust, the unit value in Rust. And all that using the unit value there means is that we're just not supplying any additional information about the error other than the fact that an error occurred. Result is yes, Sam. It's an empty tuple. Empty tuple. Thanks for the clarification, Sam. So Rust is an enum with two variants, OK and error. Internally, Rust enums are implemented as tagged unions. There's going to be a bit somewhere, possibly implementation dependent, a bit or an imaginary bit, which says either this return value is OK or this return value is an error. Our not42 function gets passed an argument named num. We then pattern match using Rust's match operator on num. If it matches 42, we return an error. If it's anything else, we return the value wrapped in the OK variant of result. Back in our main function now, we invoke the not42 function with another pattern match. This time we're matching on what variant of result we receive from not42. If we find that not42 has returned the OK variant of result, the assignment completes. If we find the error variant instead, the program panics and it's game over. Wrapping return values in a result type like this solves the problem of people forgetting to check return codes. But on the downside, this is pretty verbose. Well, fear not. The syntax you see in the main function here on this slide is flexible and powerful, and it'll be there when you need it. But for the common case, Rust provides some syntactic sugar. The snippet you see here is basically equivalent to what I was describing last slide in the main function. What calling unwrap on a result value does is return the wrapped value on success or panic on failure. That's the same thing we did in the pattern matching code in main from the last slide, but calling unwrap only takes one line instead of 4. The unwrap method is great for rapid development. It allows you to put off crafting elaborate error handling, while at the same time it leaves behind a marker that you can go back to should you need to tighten up the code later. But it gets better. Celebrate, Rust people. This code, utilizing Rust's question mark operator, is not precisely functionally equivalent to the unwrap invocation from the last slide, but let's call it morally equivalent. You'd use it for pretty much the same reasons. With what the question mark operator does here is inspect the result type and evaluate the wrapped value if the result is OK, while if it's an error, it returns the error, passing it up the call stack. That may sound vaguely familiar, because it's essentially the same behavior as the try operator from Midori and Swift. The only difference is that on error, the try operator performs an exceptional return of an error value, while the Rust question mark operator performs an ordinary return of a result tagged as an error. But that's pretty much the same thing. That's semantically equivalent. Those are two ways of achieving the same end. The question mark operator has certain advantages, though, over the try operator, or at least over Rust. Rust actually had a try macro before, which was very similar to the try operators in Swift and Midori. The nice thing about the question mark operator is that it chains better than the parens do around the try operator. Here is some admirably terse yet clear code for converting a relative path into an absolute path. You need error handling here because trying to find out what the current dir is can fail. The question mark operator performs basic error handling in a single character.
Not like Swift, it's strongly typed.
OK. Not like Swift, it's strongly typed. But let's look at this line a little more closely. We start off with a relative path. We then want to prepend the current directory onto it to get an absolute path. So we call current dir from that function from the end nodule, which returns a result. If the result is OK, the question mark operator expression, including the question mark operator, evaluates to the string value, I think. It might be a path instead, I'm not sure. Which we can then call the join method on to get our absolute path. If the call to current dir returns an error, though, the question mark operator bails out and returns that error value to the parent one level up in the call stack. The biggest practical downside to the question mark operator is that you wind up futzing around with error types a lot. This is essentially the same problem that irks programmers with regards to checked exceptions, and it has the same recommended solution. create your own error type which wraps all possible internal error types, which again is a bit of work, but it's an honest approach. It's really interesting how close Midori ended up to Rust. Even though Midori uses exceptions while Rust uses return codes, their error handling semantics are nearly isomorphic. Swift and Rust are a little more distinct from each other, but where they are similar, they nevertheless demonstrate that return codes and exceptions often have more in common than we might have supposed. In fact, all four of these platforms, Midori, Rust, Go, and Swift, seem to have evolved certain common traits. Notably, they all provide a distinct, coarse-grained error handling mechanism for bugs, which is separate from their fine-grained function-level mechanism for recoverable errors, and they all ensure that locations in the code where failure can occur are identifiable, shunning the invisible control flow, which makes many exception-based environments difficult to reason about. Each language gets one shot at an error model. Once a language gains traction, changing the error model becomes impractical. Taking a cue from Rust, Java introduced the optional type several years ago, but it has not exactly set the Java world on fire. Even if you introduce support for newer mechanisms, culture is durable, and culture is largely determined by the APIs of a language's standard library. You're not going to break legacy standard library APIs wholesale, even if you go to the extreme of introducing new ones. And there will continue to be vast quantities of legacy code written with the language's original error model as a template. And so we should expect the ongoing evolution of error models to be slow, with large steps occurring infrequently at the pace of new languages gaining critical mass. Thank goodness that there has been enough progress before today to give us systems like those in Go, Rust, and Swift, and Midori, which are more pleasant to work with thanks to the explorations and lessons learned from those who have gone before. Thank you.